Hi, today we are going to take a look at this digital flux gate heading sensor. The power supply is 12 volts. There is an output compliant with NMEA 0183. We can see here two electronic boards, and the flux gate sensor is here on the bottom. This is the flux gate sensor. So let's start by the sensor, which is the main part of this unit. We have here a ring core flux gate sensor. Actually, in the middle here, it is difficult to see. We have a ring core, which is made with saturable material. Generally, it is made with permalloy. You can see here the ring core. We have two different coils. The coils in grid is actually the excitation coil. We can see that the excitation coils here are wound around the core. There are 4 coils in series, the green ones here. And we have 2 pickup coils, but these coils are actually all around the core. It permits the measurement of the variation of magnetic flux. Okay, it is something similar to that image here. This is a 2-axis ring core sensor, except that on that image we have only 2 excitation coils and we have 2 pickup coils. So the goal is to saturate the material. So the material is made with permalloy generally. So therefore there is a variation of flux around the core, because when the core is not saturated, the magnetic field is concentrated inside the core here. But when the core saturates, the core doesn't exist anymore, and therefore there is a magnetic field which is present all around the core. And the variation of flux is detected by these 2 coils here. When there is no external magnetic field, the saturation is symmetrical. But if there is an external magnetic field, the saturation is not symmetrical anymore, and therefore there is the presence of second harmonic across these 2 coils, depending on the orientation of the external magnetic field. We can see here in the center the connection of the flux gate sensor. You can see that we have 2 connections here, black and red. This should be the excitation coil. And we have here the connection to the pickup coils X and Y. Generally, the detection uses a synchronous detector. This is probably this circuit here. The synchronous detection works at a frequency which is twice the excitation frequency. On that board, there is a microcontroller here. We have here a static memory. So we can see the frequency of that crystal, 11.0592 MHz. So this is the typical crystal frequency for an 8051 from Intel. So this part should be an 8051. There is here an EEPROM, which is used certainly for some calibration data. We have here an analog section. So we can see here a dual op-amp. We can see here an analog multiplexer, 1 to 8. We can see here another analog multiplexer, a triple, 2 inputs, 1 output. So I guess that at least one part is used probably for the phase detector. This is the typical part for that purpose. And we have here 2 quad op-amps, LF347. There is an oppo coupler. We have here an HC173. So this is a quad D flip-flop. Here we have a latch. We can see that there is a connector which is not used, which is connected to this latch. We have here a 138 for the address decoding. This is an HC00 quad NAND gate. So let's see the second board. Second board is here, so we can see several latches here. We should have the data bus connected here to that header. Here we have an RS-232 interface part. Here we have an analog circuit, with several op-amps. Here we have a connector which is not used. It is connected to a ULN2003, which is an array of transistors. Here we have another analog multiplexer, triple, 1 input, 2 outputs, several transistors here. And here we have an 82C53. This is actually a timer. We can see here the main circuit of this flux gate transducer. We have here a virtual ground circuit which generates a voltage of plus 4 volts. So here we have a voltage regulator which delivers the voltage of plus 8 volts, which is used for more or less all circuits. There is here another voltage regulator which delivers the voltage of plus 5 volts for the digital circuits. Here we have a dual slope ADC. We have on the left here the circuit for the excitation of the flux gate sensor, which is here. We have here the main circuit which permits the extraction of X and Y component of an external magnetic field. This system uses a magnetic feedback. We can see that we have two identical circuits, one for Y axis, second one for the X axis. The flux gate sensor is here. We have 4 excitation coils in series, and we have 2 pickup coils orthogonally placed. Each coil has actually 2 different functions. One function is to sense the second harmonic. The second function is to generate a magnetic field which will compensate the external magnetic field. If the sum of the external magnetic field and the magnetic field generated by the coil is not zero, there is here a second harmonic signal. This error signal is amplified. You can see that we have 2 amplifiers in cascade. The gain is 100, and this signal is fed to this phase detector. At the output, there is a DC component. This DC component is fed to this integrator. The voltage at the output of this integrator is converted into a current using this feedback resistance, and this current will generate a magnetic field. At the end, when the second harmonic here disappears, the magnetic field generated by the coil here is identical to the external magnetic field. Therefore, the output voltage here is an image of the magnetic field. We can see here the dual slope ADC. The integrator is here. There are several inputs which can be selected using this multiplexer. These 2 inputs are not used. The third input here is used to sense the power supply input voltage, plus VA, which is normally plus 12 volts. Input number 3 here is used for the measurement of the Y component of the magnetic field. The next one for the X component. The next one here is used for the measurement of the zero, so this is actually the virtual ground. This input is connected to the output of this integrator, so this permits to discharge this capacitor here. This capacitor is here. It's a good capacitor, probably NPO. We can see here the functioning of this ADC. First, there is a discharge of the capacitor during 1 millisecond approximately. After that, there is an integration during a fixed time of the input voltage. There is an increase when the input voltage is below 4 volts, and there will be a decrease of the voltage if the voltage is above 4 volts, which is a virtual ground. And after that, there is a hold time, so this permits to change the configuration of the switch. And after that, there is an integration of the reference voltage, which is actually 1 volt, and this occurs until the output of the integrator reaches the voltage of 2 volts approximately. And of course, this time is measured by the microcontroller. From this time, it is possible to calculate the input voltage. We can see on the screen of the scope here the output of the integrator, this signal here. We can see that we have 4 measurements. The first measurement here is the 0 measurement. We have here the 2 measurements, X and Y, or Y and X, I don't know. And the last measurement here is the power supply measurement. Currently, the power supply is set to 12 volts. I'm going to increase the power supply. Okay, so we can see the change here. I am decreasing the power supply. $7 volts. We have here the discharge of the capacitor. There is here the integration of the input voltage during a constant time, which is approximately 400 microseconds. There is a hold time here, and there is here the integration of a reference voltage of 1 volt down to this voltage, which is approximately 2 volts. We can see on the screen the reference signal for the excitation. This is the square wave, 50% duty cycle. Frequency is 5.4 kHz. And we have here the reference signal for the phase detector. The frequency is twice this frequency, approximately 10.8 kHz. We can notice that the duty cycle is not exactly 50%. I guess that the duty cycle is set in order to adjust the phase of the fundamental of that signal in order that this fundamental is in phase with the second harmonic of the sensor. This permits to increase the sensitivity of the detection. We can see on the screen here the reception of the message according to the standard NMEA 0183. The value of the heading is here, and there is a checksum at the end. Currently the heading is 71.6 degrees. That's all for today. Thank you for watching and see you next time for another video. Bye bye.